We are in our last chapter, chapters 7. We're going to do sections 1 and 2. Today we'll look at sections 1, trigonometric identities. This section, I always say, is great for those of you that like problem solving and games, because it is similar to that when you're solving these identities. So we're going to look at simplifying trigonometric expressions and then proving trigonometric identities. And here is your big information center where you need to know. Again, you've already known that cosecant is 1 over sine, secant is 1 over cosine, cotangent 1 over tangent, and that tangent and cotangent functions are sine over cosine and cosine over sine respectively. The Pythagorean identities we've already looked at, been tested on, know how to get those identities. So those are important in this section as well. Even odd identities, also we've already worked with. Sine is a odd identity, cosine is an even identity, and because tangent is sine over cosine, that would make it an odd identity. The only ones we haven't looked at yet are the cofunction identities. So here we have our sine of pi over 2 minus whatever radian we have here will be equal to the cosine of that. So these are some new identities that you need to spend some time looking at. Frankly, a lot of times these are available for your reference, so they're not really something that you have to memorize. However, knowing is always better than having to look it up. So if you know these here, like you know the above, assuming that you do know the above at this point, you definitely should, then it'll be much easier for you. So take some time to understand these identities, these cofunction identities below, and how they are related, and that will save you a lot of time, energy, and, well, time and energy. That's the big thing. So here you go. All right. So let's look at simplifying trigonometric expressions. Now, identities enable us to write the same expression in different ways. It's just like reducing something. Whenever you had geometry, you might have done some proofs where you could substitute in one thing for another because you knew that something was equal to another thing. It's the same kind of idea. I don't want to scare you by saying geometry proofs, because they're not like geometry proofs to where you have to state your reason every time you do a substitution, but you will be substituting in one thing for another, knowing that they are equal to each other. So let's take a look. Here we have cosine plus tangent times sine. So we want to see how we can simplify this expression. Now, in order to simplify, a lot of times, not all the time, but a lot of times it's easier to take the trig expressions and change them to sine and cosine. So if I change my tangent to sine and cosine, then this becomes cosine t plus sine t over cosine times sine. Now, I'm looking at this going, well, let me multiply this and see if it makes any difference. And now I have my sine t times sine t is sine squared. And then if I here change this to a common denominator, I'm going to place my cosine over 1, which means I have to multiply the top and the bottom by cosine. So when I multiply my top and my bottom by cosine, I then we'll have the common denominator of cosine and can write cosine squared plus sine squared over cosine. Now, cosine squared plus sine squared, immediately when I say that, you should be like, wow, that's equal to 1, because that's one of the Pythagorean identities. And that's exactly what we're going to do next, is we change it to be 1 over cosine t. Now, depending on what you're doing, you may want to leave it 1 over cosine t, or you might want to change it to be secant t. If you're changing it just to be as simple as possible, it would be secant. Now we'll take a look at proving trig identities. So again, the same thing that we talked about before is if you have something that you know is equal to another. In other words, the last example that we did, we had sine squared plus cosine squared equaled 1. So I could substitute 1 in for sine squared plus cosine squared. So now we're going to take a look at using these ideas to prove trig identities. So what we're going to say is we're going to show that one side does in fact equal another side. So in sine x plus cosine x equals 1, this is not an identity. So we see that pi over 4, if I plug that in, I am not going to get one side equal to another. So we have to verify that an equation is an identity first. And the only way we can verify that is if we make one side equal to the other side. So what am I saying here? So I am saying that if I have a problem like this side, if I can make it look like this side, then it's an identity. If I can't, then it's not an identity. So the ones that we will be looking at in this section are ones that are identities, but you have to show how those are identities. So we start with one side, we use the known identities, and then usually if you get stuck, you can convert to sines and cosines, as I mentioned before, and a lot of times that makes it a little bit easier. So here I have cosine times secant minus cosine equal to sine squared. We want to see, is this true? Is this an identity? That's what I say when I say, is it true? Does this side equal this side? So we want to start to see if we can transform this side, which we call the LHS, which simply stands for left-hand side. Kind of unnecessary, really, I think. LHS. So we want to say, is the left-hand side going to be equal to the right-hand side? Okay, so I want to see if I can change cosine times secant minus cosine to be sine squared theta. Okay, and again, this LHS just means left-hand side. So I'm going to change this to be 1 over cosine. Again, this is a strategy that you can use. You don't have to use this strategy right away, but a lot of times changing everything into sine and cosine will make things a lot clearer when we're looking at identities. So if I multiply that through, I will get 1 minus cosine squared equals theta, because my cosine's reduced to 1, and now I have this. And I should look at that and say, that looks a little bit familiar. And I want to see if that will equal sine squared. Well, it does. And how did I get that? Okay. So let's take a look here, and we go back to my pen, try to write this out as neatly as I can. If I have sine squared plus cosine squared equals 1. And sorry about my writing. I need to get something that's a little bit easier to write on these. Okay, equals 1. And I say, oh, I have 1 minus cosine up here. So if I take cosine and I subtract it from each side of this Pythagorean identity, then I am going to get sine squared equals 1 minus cosine squared. So once I have that side and I'm showing that sine squared does equal to 1 minus cosine squared, then I can substitute it in for that. So what I did is I took the Pythagorean identity that I know and I changed it to look like this. And I see that it is equal to sine squared, and then I can multiply it in. And guess what RHS means? Right-hand side. Now they're going to show you if you graph the equation, and let me erase this stuff out of the way so you can see what they're talking about here a little better. If you graph the equation on each side, you can see where they coincide. So they're showing you that if I graph cosine theta times secant theta minus cosine theta, and I graphed sine squared theta, I get the exact same graph. So that's what we're talking about, is basically saying that one equals another. Another way to look at this is if I asked you, and this is completely separate, but if I asked you 6/8, and I reduce that 6/8 by 2, and I get 3/4. 6/8 and 3/4 look different, but they're the exact same value. And that is exactly what we're doing here, is we have two things that look different, but they're the exact same value. Okay, so in here they're talking about example 3. Might not be as easy, but sometimes you have to work backwards from one side to the other. So let's take a look. And example 5, they do something that's extra. Let's see if we're going to look at that. Here we go. Example 5. Cosine u over 1 minus sine u. That is equal to secant u tangent u, or we're asking you to prove that it's equal to. So when you're proving this, you're going to assume that it is so that you can solve. Now notice this cosine is over 2 terms, so I can't split this up to be cosine and then sine over u. Please don't make that mistake. It's only if it were the other way around if I could put both terms under the other one. So here we have our left-hand side, which I'm not a fan of just writing left-hand side. I think it's unnecessary, but if it helps you, that's fine. I am going to multiply this by 1 plus sine u, 1 plus sine u. Why am I doing that? Well, again, if I know really well that cosine squared plus sine squared equals 1, then I know that 1 minus sine squared equals cosine squared. So if I see something like this, I can use this strategy here to simplify to get 1 minus sine squared on the bottom. So now I have 1 minus sine squared on the bottom, and guess what? 1 minus sine squared is going to equal cosine squared, so now I can substitute in that. Now that I have this, I can actually reduce a cosine And I have 1 over cosine plus sine over cosine. Now, I know that 1 over cosine is equal to 1 over secant. See, they just did right here what I did there. So that will reduce to be secant, and the other will reduce to be tangent. Is that what I wanted? It is. So in the last problem, we got the one side equaling another. Here's another method for proving that an equation is identity. We can transform each side of the equation separately by way of identities and achieve the same result. Now this would be when both sides are kind of complicated. So here I have an identity that's kind of complicated on both sides, and we're like, I don't know which side to start with. Well, you can work on both sides separately to try to get them to a simpler thing. So the first one, we're going to show that if I take 1 plus cosine over cosine, I get 1 over cosine and cosine over cosine, which reduces to secant plus 1. Now, if I can reduce the other side to secant plus 1, I have tangent squared over secant minus 1. Now, I remember by my Pythagorean identity that my secant squared minus 1 is tangent, so I substitute it. And that's a difference of squares. Hopefully you made that connection, and can be factored to be secant minus 1, secant plus 1. So if I can reduce this, then I will get secant plus 1 on this side. So now both sides are the same, and what I did was simplify the left-hand side and the right-hand side to be the same. An example of this might be, let's say I have 10 15ths. And let's say I have 50 over 75. And I want to know if that is equal or not. Well, the first one will reduce by 5, and I will get 2/3. The second one will reduce by 25, and I get 2/3. So it was easier for me to reduce both of those and show that they're the same than to try to make one of them into the other. So in conclusion, we describe this technique of trigonometric substitution, where we convert algebraic expressions into trig ones. Useful in calculus when finding the area of a circle or an ellipse. Anytime that you have something more complicated and you can make it more simpler, is definitely an advantage. So let's take a look here. If I have sine of theta and this expression of the square root of 1 minus x squared, we're going to assume that the theta is between 0 and pi over 2. Why am I doing that? Because I have positive and positive for my sine and cosine in quadrant 1. So I can see that I could actually make this the square root of 1 minus x squared equal to the 1 minus sine squared theta. And that would be the square root of cosine squared theta, which would equal cosine. So it's true because cosine theta is greater than or equal to 0 for all values. And that is all for section 7.1. And I'll see you for the last lesson soon.